Here's a solutions summary for exam 3. On problem 1, you were asked to use vector math to find the acceleration of point C. And you were either given a positive or negative velocity and acceleration here at point A, and an angular velocity and an angular acceleration. The thing that you need to recognize is that this is one solid rigid body, so you just need to look from C and A right here, but you should probably find or you should find the length of C to A. So we'll start off with the knowns. Here are the things that were given. I called this angle beta. That was that's formed between A and C. If you're going to compare it to the length of A and B, right there, that's beta. And then I get the length in between A and C. So to get the relative position vector, then you take that LAC and multiply it by the cosine of theta that you were given plus beta. And notice that the x and the y are both negative in the negative direction because we're pointing to C from A. So it's C with respect to A. So we put this into the cross product formula here. And remember, this is the translational part. And this is the angular acceleration times that relative position vector. And then you subtract out the magnitude squared of the omega times the relative position. So if we work through all of those, make sure you keep the signs correct, and then we distribute the cross product. That's like the important part. So this turns into positive j, this turns into negative I, and then we put them all together, and this is what the components are. So you can make sure that you look at the numeric summary to see which values that you were supposed to come up with. For problem 2, this was to use the instantaneous center of rotation method. So when we start off with, we were given an angular velocity of omega on link AB. We're going to assume, I'm drawing it as if it's positive, but you might have had a positive or a negative value right here. So we find that velocity of B with omega AB times LAB. And then we're going to use that over here. And the very most important part is to find the instantaneous center of rotation. And you can see that's where the legs of the links, lines of them, where they merge. And from the angles that were provided right here, you could find that this interior angle is theta B plus 90. This interior angle is theta D minus 90. If you take a look, and you'll be able to work that out. And then this third angle right here is just going to be 180 minus theta B minus theta D. And so we could get using the law of sines, we're able to find what the relative position vector is from B with respect to ICR using those interior angles. And then we're able to find what omega BC is by taking the velocity of B that we found up here and dividing it by the leg of this ICR. We also want to use the law of sines to find the velocity here at C. So we find that ICR, and then we use that omega that we just found at BC to find the velocity of C. Now we use that velocity of C to find the omega of this link. And then with that omega, we're able to find what the velocity of E it was. So that was our goal in part here. So this was purposefully made this a problem where you had to think your way through a number of steps to get to the end. And okay, so here is the answer right there is the velocity at E, and it had to be at that angle because we were asking for the angle and the quadrant. Okay, so problem 3, we're doing an acceleration problem where we start off, we're given with a angular velocity of this link. And from that, we can get the normal acceleration at B. Now, sometimes I might break this down into the X and the Y component. I think I did that in the spreadsheet. But here I just went ahead and kept it as a value and then looked at the angles for the thing. So we get the magnitude of that. And then here's the 3-diagram method for this link BC. Here's that acceleration at B that we just found. We place it onto both spots, and then we pin it to where it is right here. And then I made an assumption that the angular acceleration is going to be counterclockwise. We were given the angular velocity here, so we can get this normal acceleration right here. And if we write out the equation for this top point, that's the acceleration of C is equal to the acceleration of B plus the tangential acceleration plus the normal acceleration, the relative one. So in the Y direction, which is probably the easiest, this is the way to go first, because then we're going to be able to get the angular acceleration, because there's no acceleration in the I just said that wrong, didn't I? Yes, no, I said it right. Okay, yeah, in the Y direction. There's no acceleration in the Y direction. And so you could see, let's see, as we're walking through this, we'll see that this is a positive value of AB. And we're using the sign because it's the opposite from that angle. And for the acceleration, as we've drawn it right here, we see that it's positive, and it's going to be the cosine of theta C. And normal is going to be negative. It's going downwards. We're going to see this is going to be the sine of theta C right there. So working that all around, we're able to get what that angular acceleration is going to be. And then in the X direction, we're able to put that into place. Making sure, let's see. Okay, this is positive. Yep, it's in the positive X direction, and it's the cosine of theta B. Yeah, and this depends on whether this was positive or negative. By the way, it depends on what the values were like of this. It could become negative if this was large enough. By the way, this alpha BC. But then put these values in. Make sure that you make this sign based on what the diagram is, and then if we had this one became negative, then you also put it in as negative, so the negatives would cancel out. And then this one was also in the negative direction here, and with the cosine. So there you go. That was the exam. Have a good night.